three papers, so each will be roughly 20 minutes. The first paper is on almost optimal stochastic weighted matching with few queries, and this is going to be presented by Soheil.
Thank you for the introduction. So yes, I'm going to be talking about almost optimal stochastic weighted matching with few queries. This is a joint work with Nima, Reyhani, and I'm Soheil Behnezhad. Okay, so I'll start with the definition of matching. You're given a graph G, and a subset M of its edge set E is called a matching if no two edges in M share an endpoint. So for example, this, I should get closer. So for example, this subset of the edges is a matching, and a maximum matching is a matching with maximum size, right? The natural generalization of matching to edge-weighted graphs is to consider the sum of the weights written on the edges, right? So in an edge-weighted graph, a maximum weighted matching is a matching where the sum of the weights of the edges in the matching is maximum. And there has been a lot of fundamental research on finding maximum matchings in different settings, including massive graphs, online graphs, dynamic graphs, etc. And our goal here is to find an approximately maximum weighted matching in a stochastic graphs with few queries. Before describing the actual model, I will start with an application in kidney exchange. So transplant of a kidney of a living donor is possible if the patient is medically compatible with the donor, right? But even if they're not compatible, what we can do is to take two incompatible donor-patient pairs and swap the kidneys that they have, right? So the donor of one pair swaps kidney with, transplants his kidney or her kidney to the patient of the other pair and vice versa. And this is the simplest form. You can think about having chains or cycles or something like that. Okay, so we can define sort of a compatibility graph. And what this compatibility graph really defines is a graph where each vertex denotes a pair of donor and patient that are incompatible to each other. And we put an edge between two pairs, between two vertices, if they can swap kidneys, right? So based on our initial knowledge about blood types, tissue types, etc., we can rule out some edges, right? So for example, we can determine that these two pairs cannot swap kidneys because the blood types are not, say, compatible. And a matching in this graph specifies the pairwise swaps, right? So we want to be able to find a large matching in this compatibility graph. But the main problem really is that this initial knowledge that we have about blood types or tissue types, etc., is not sufficient to be able to know what the actual compatibility graph really is, right? And to handle this, what's really done is that we need extra expensive medical tests to confirm that, yes, these two pairs can actually swap kidneys. So the actual compatibility graph is much sparser than the graph that we really, at the first stage of the algorithm, think the compatibility graph is. And what we can do is to say we can query each edge to see whether it really exists in the graph or not. OK. So let's get to the actual theoretical model for this. We are given a graph G with edge weights on with positive edge weights on the edges. And we are also given a parameter P between 0 and 1. And for the application of kidney exchange, the weights are important because they can take into account considerations such as degree of compatibility, wait time, geographic proximity, and so on. Okay, a realization of graph G, which we call G sub P, is initially chosen by nature, where each edge in G appears in the edge set of G sub P independently with probability P. right? So we're unaware of this realization graph G sub p and its edges in E sub p. Yet our goal is to compute a maximum weighted matching, an approximately maximum weighted matching of G sub p. And OK. Good. And to do this, we can query the edges to determine whether they exist in the graph or not, right? Other applications of this model include, say, online dating websites, applications, or online job markets where you want to really minimize the number of interviews that the freelancers they have, right? OK. So let's see some algorithms and compare them to get an idea about the model. So one algorithm is to, say, query all the edges and just report the maximum weighted matching in the realized graph. The good thing is that we find the exact solution. We find the maximum weighted matching of the realization graph. But obviously, this is not good because it's going to query every edge. And we can't afford that. Another approach is just to take a maximum weighted matching and query its edges. The problem with this approach is that the only approximation factor that you can guarantee is our realization probability p. Because if you take a matching, only a p fraction of its edges are going to realize, right? But the good thing is that we query only one edge per vertex, right? So the main question really is, can we combine these two factors and get a near optimal solution with very few queries per vertex or not? OK. There are two algorithms there are two regimes for algorithms in this setting. One is non-adaptive algorithms, where you essentially just pick a subgraph H of your input graph G, query its edges, and report the maximum weighted matching among the edges that are realized. Adaptive algorithms, on the other hand, can have multiple rounds of adaptivity. So in one round, you query a set of edges. And once you see the outcome of those queries, in the next round, you decide which edges you want to query, right? So as you can imagine, adaptive algorithms are simpler, probably, to get to an almost optimal matching, right? Because you have more information. In non-adaptive algorithms, you have literally no information about the realization. You just want to pick a subgraph and find its matching. OK, so this was first formalized by Blum et al. And they showed that, indeed, an adaptive algorithm can obtain a 1 minus epsilon approximation of maximum matching. This is only for unweighted graphs. And they also showed that an almost half approximation can be achieved with a non-adaptive algorithm. And the good thing is that the number of queries per vertex is only 1 over p to 1 over epsilon. So if you think about it, this 1 over p is really a small number, say, in the kidney exchange. This is a constant. And 1 over epsilon is also a constant. So this is good because you only query a constant number of edges per vertex and get an almost optimal matching. Later, Asadi et al. Improved this result to get a dependence of almost linear in both epsilon and p. So they further showed that in 1 over epsilon p, with only 1 over epsilon p queries per vertex, you can either get a 1 minus epsilon approximation with an adaptive algorithm or a half approximation with a non-adaptive algorithm, right? And later, Asadi et al. Next year showed that one can get a slightly better than half approximation with a non-adaptive algorithm. This is what's known about the unweighted graphs. For weighted graphs, the only result known prior to our work was the recent paper of Mahara and Yamaguchi. And they showed that the same approximation factors can be achieved. And the dependence on epsilon and p is similar to this bound that Asadi et al. Give. But the problem here is really that there's a dependence on the maximum edge weight, where you assume that all the edge weights are integers. And it also depends on the size of the graph. So the question really is, can we achieve the same approximation factors with only a constant number of queries per vertex or not? And our contribution is to show that with 1 over p to 1 over epsilon queries per vertex, we can indeed achieve this approximation. This is not as good as the bounds known for unweighted graphs, but the good thing is that it's constant. And it's independent of the structure of the graph, the weights, etc. Okay. So I'll focus on the adaptive algorithm. The algorithm is actually really simple. So what you do is to just take a maximum weighted matching, query its edges. If you see that some edges are not realized, you just remove them from the graph. You again take a maximum weighted matching and query its edges and so on. So the number of edges per vertex that you query is really the number of rounds that this algorithm takes, right? And in the end, you just report the matching, the maximum weighted matching among the edges that you have queried so far and are sure that are realized. So you select a subset of edges, query them, remove the ones that are not realized from the graph, and continue this until you find a matching that's large enough. And this is, interestingly, this algorithm is really, almost every paper on this problem uses this algorithm, and the main difference is really in the analysis of the performance of this algorithm and how many runs are required to achieve our desired bounds. Okay. So I'll start with a set of definitions. You're probably familiar with this. If you have two matchings, M1 and M2, an alternating path is a maximal path that alternates between the edges of the matchings, right? And an augmenting path is an alternating path that if you swap the edges, the base matching size increases in the unweighted graphs, right? And for unweighted graphs, we know that if M1 is, the size of M1 is less than 1 minus epsilon fraction of M2, then if you look at these augmenting paths, there are many augmenting paths that have a constant size, right? So inspired by the algorithm of Blum et al., I'll just show that why that algorithm achieves a 1 minus epsilon approximation for unweighted graphs, and then I'll describe how we can generalize that to weighted graphs. So let us denote by O sub r the largest weighted matching that we have found by round r. And this is the output of the algorithm. So in each round, we pick a maximum weighted matching, maximum matching M sub r, right? This M sub r can be shown to be always larger than opt, because every edge that remains in the graph will always be in the graph among which you find a maximum matching, right? So if your O sub r is smaller than a 1 minus epsilon fraction of M, then you will end up with a lot of small augmenting paths. And if you take one augmenting path, if all of its new edges are realized, you will add add 1 to the size of your realized matching, right? So really what happens is that all of the edges of an augmenting path with size 1 over epsilon are realized with probability p to 1 over epsilon. So roughly in 1 over p to 1 over epsilon rounds, you will achieve a 1 minus epsilon approximation. Our goal is to follow the same approach for the weighted graphs. And this is why we get a similar bound. But the problem really is that in weighted graphs, you may end up with only one augmenting path that's really long and has a really large difference between the two matchings, right? So the argument of having a lot of small augmenting paths does not really carry over to the weighted graphs. And this is one of the reasons that augmenting paths are not really used for weighted graphs in the literature. And so what we do is to relax some assumptions. So we take two matchings. In weighted graphs, we don't necessarily have augmenting paths. We may have cycles that are augmenting, right? So we call them augmenting components. And for component C, we define 3 properties. One is the amount of weight that it adds to the matching. One is the set of edges of the larger matching that are part of that component. And third, we define the normalized length of an augmenting path to be the weight of its larger matching portion over delta, which is the amount of weight that it adds, the difference between the weight of the edges of the 2 matchings. And we show 2 properties. First, that querying the edges of an augmenting component C increases the weight of the maximum matching in expectation by at least p to normalized length of that augmenting component times its difference, its delta. And there's always a set of augmenting components that have a small normalized length, right? So this generalizes that to the weighted graphs. And to do this, really to give the intuitions behind why this works, take an augmenting component C if, and denote by k its length. If this length is smaller than its normalized length, then with probability p to k, we realize the whole path and we're good. But if the length of the component is really longer than the actual normalized length, what we do is to decompose the component into smaller pieces and show that if each of these smaller pieces is realized, then we add a good expected value to the weight of our realized matching. And that's it. For the second part, take an augmenting component C if its normalized length is larger than 1 over epsilon. What we get is that its delta is much smaller than epsilon fraction of the edges of the heavier matching. So in some sense, we are wasting a weight of WQ sub C from the whole heavier matching without contributing much to the whole difference. And that's it.
We have time for a couple of questions.
So I have a question. One is, it seems like in the model, right, what you want to get is a large matching where each vertex suffers a small cost, where we have some idea that like the cost to a vertex is the number of times I have to query an edge adjacent to it, right?
Yeah.
What if those costs aren't uniform? Would all of this fall apart if all of a sudden I said now the cost when I query an edge to the neighbors, the 2 vertices, the endpoints, is somehow like related to the weight of that edge? Would you be able to adapt any of this, or would that somehow break everything? Does that question make sense? So
we would have to change the algorithm somehow, right? Because we don't take into account any sort of cost on a specific vertex, right? So you would have to appropriately change the algorithm and come up with an argument that, yes, this somehow respects those.
It's not really hopeless that you could do well on both like some more general cost model and the maximum matching kind of criterion, right?
Yeah,
It seems like you could adapt something to this.
probably yes. Yeah.
Okay, maybe, yeah.
Yeah.
Too abstract of a question.
Yeah. Yeah.
So any thoughts if the value distribution is not Bernoulli, but some other distribution?
Yeah, so if the weights are not really different, then the arguments used in unweighted graphs, some of them can be adapted to weighted graphs. But if the edge weights are really different, I'm not sure how distributions can really help. Because we are given all the weights at the start of the algorithm, right?
Yeah, but
You're saying that after realization, maybe we know the.
realization is not Bernoulli 0 or the value.
Yeah,
No, it's some
I see. Yeah, I'm not sure about that.
So you really wanted to avoid the dependence on W, right?
Yeah, and N.
Yeah, so I'm just wondering if you were okay with the dependence on W, but you didn't want N. Could you have gotten like what Asadi et al.'s guarantees are, or something similar to that, rather than the exponential guarantee of Blum et al.?
Yeah, I'm not sure about that. Yeah.
And then, can I ask a second question?
Yeah.
One of the differences between the exponential guarantees and the polynomial guarantees in the algorithm is this vertex classification lemma.
Yeah.
Is that one of the challenges that you have in getting a slightly better guarantees, or no?
I don't think sparsification lemma of Asad et al. Is a problem because in the paper of Yamaguchi and Mahara, they have a notion of vertex sparsification as well. So yeah, I don't think that's the barrier really.